Good day all. Today we are going to learn from this session Moving Charges and Magnetism and Magnetism Matter. So these are all the two chapters regarding magnetism, that is chapter 4 and 5 together we are going to see. Yes, so students, chapter 4 Moving Charges and Magnetism, the syllabus they have given for this year, concept of magnetic field, Oster's experiment, and Biot-Savart law and its application to the current carrying circular loop, Ampere's law and its applications to infinite long straight wire, straight and toroid solenoids, force on a moving charge in uniform magnetic and electric fields, force on a current carrying conductor in a uniform magnetic field, force between two parallel current carrying conductors. From that we will ask definition of the ampere and torque experienced by a current loop in a uniform magnetic field, moving coil galvanometer and its current sensitivity, voltage sensitivity, conversion to ammeter and voltmeter. They have omitted in this chapter only cyclotron. So all other than that the topic you have to concentrate. In chapter 5, Magnetism and Matter, current loop as a magnetic dipole and its magnetic dipole moment, and magnetic dipole moment of a revolving electron. Then you have to know and concentrate on bar magnet as an equivalent solenoid, magnetic field lines, Earth's magnetic field and magnetic element. See children, in this chapter they have deleted so many subtopics. You have to know that very carefully. The magnetic field intensity due to a magnetic dipole, that is a bar magnet along its axis and perpendicular to its axis also is deleted. And torque on a magnetic dipole, para, dia, ferromagnetic, that is the magnetic substances with the examples, and also electromagnets, that is factors affecting their strength, permanent magnets, these and all they have deleted from this chapter. Yes students, now we can know about the formulae, that is from chapter 4 and 5, Moving Charges and Magnetism and Magnetism and Matter. From that the B vector which is equal to mu naught 4 pi ideal R cap whole divided by R square, that is for the Biot-Savart law, right. Then next one is the unit of magnetic field, Tesla, and the formula which is given Fm which is equal to Q naught, V vector cross M vector for the Lorentz force, and that is next one is the magnetic field due to a straight solenoid, B which is equal to mu naught Ni. So that is also for, we can say that, the toroid. For the toroid formula also we can say that the B which is equal to mu naught Ni, that is for the, this is for the straight solenoid, that is for the circular loop. And Ampere's circuit law, closed integral B vector dot dl vector which is equal to mu naught I, that is one formula. And here this is for magnetism and matter, tau, that is torque on a magnetic dipole in a uniform magnetic field, tau which is equal to mb sin theta. And this is the formula for the magnetic force between the parallel infinite current carrying conductor. If suppose it is in the same direction, we can get it F which is equal to small fm by L, that is capital F which is equal to mu naught 4 pi 2 I1 I2 by R. So that is the formula. And this is for the moving coil galvanometer. If suppose the current which is directly proportional to the deflection, then I which is equal to K by NBA theta. So these are all the formulae you must know from the chapter 4 and 5. So question number 1, write the condition under which an electron will move undeflected in the presence of the cross field. That means the cross field which means what? Electric and the magnetic field. That we can say that V which is equal to E vector by B vector. That is nothing but the electric field by the magnetic field, we can say that, or else alternatively we can say that F, that is modulus of Fb which is equal to modulus of Fe, that is force on the Lorentz force of magnetic field which is equal to Lorentz force which is equal to the electric field, we can say that. So the question number 2, deduce the expression for the frequency of the revolution of a charged particle in a magnetic field and show that it is, that means that is independent of the velocity, or we can say that the energy of the particle. You have to show that it is the independent of velocity, right? So we can say that when a particle of mass m or charge q, which is moves with a velocity v in a uniform magnetic field, means definitely it will experience a force F. So we can say that the force F, which is equal to F vector, which is equal to Q into V cross B. So that V cross B, we can say that then the centripetal force. So the centripetal force formula is what? Centripetal force mv square by r, which is equal to, we can say that qvb, that is the horizontal component, right? So qvb. So then we can say that the r value, which is equal to mv whole divided by qb horizontal, right? That is for the horizontal component, or we can say the perpendicular, b perpendicular, we can say that. So here we can say that the frequency of the independent component, what they asked, the independent of velocity, frequency of the independent of velocity or we can say energy, that is equal to what it will come? It will come that V by 2 pi r, which is equal to QB by 2 pi B. So this is the formula for that independent velocity or the energy of the particle, right? Yes, next question. Show how Biot-Savart law can be alternatively expressed in the form of Ampere's circuital law, and use this law to obtain the expression for the magnetic field inside a solenoid of length L, cross-sectional area A, having a number of closely wound turns and carrying a steady current I. Draw the magnetic field lines, an infinite solenoid, current carrying I. So we have drawn that. They have given about the magnetic field lines of a finite solenoid current carrying wire. See, actually children, we can say that any surface which is carrying current, that can be divided into a small lines. That is only we have drawn that small lines, the element, and that we have given that it has a length L, right? So this can be expressed, and we can find here the magnetic field, that is B dot dl, right? And the sum of the elements of the individual elements we have taken, that we can say that closed integral B dot IL, B dot dl, which is equal to mu naught I, that we know that, right? So that mu naught I, the current which is carrying through this magnetic field lines, we can say that the current NHI, right? So the total enclosed current which is through the magnetic field NHI, as we know that the magnetic, some of the element tends to the integral, closed integral B dot dl, which is equal to mu naught NHI, right? So that we can say that BH, which is equal to mu naught NHI, right? So B here we have ruled out the H value, so that B, which is equal to mu naught Ni, we got it, right? So this comes under the Ampere's circuital law. We have expressed the law in the integral form. From that we got the value B, which is equal to mu naught Ni. This next question. State the principle of working of a galvanometer. The subdivision of question, a galvanometer of the resistance G is converted into a voltmeter to measure up to V volts by connecting a resistance R1 in series with the coil. If a resistance R2 is connected in series with it, then it can be measured up to V by 2 volts, right? So find the resistance in terms of R1 and R2, which is required to be connected to convert into a voltmeter that can be read up 2 volt. See, which you are going to convert that can be read up to 2 volt. So also you have to find out the resistance G of the galvanometer in terms of R1 and R2. The conversion type they will ask 2-3 years that consecutively, right? So you must know always the principle of the working of the galvanometer. So this is the principle of the working of galvanometer, a current carrying coil which experiences a torque. If suppose it is experience a torque, when it is placed in a magnetic field, it will tends to rotate the coil and it produces an angular deflection. That is the galvanometer working principle. And they have given, you have to convert it. So when you are going to convert, you must know V, that is voltmeter V, which is equal to I into G plus R1. Here for the R1, and also we must know about the R2. For that they have given, it can be measured up by V by 2. So that V by 2 which is equal to I into G plus R2. By comparing that 2, we will get 2 which is equal to G R1 by R2. Sorry, G plus R1 whole divided by G plus R2. So G, by simplifying this, we will get G which is equal to R1 minus 2 R2. Got it? Now, here you must know R3, that is the R3 that can be the resistance. If we need means to convert into the voltmeter which can be read up, what is the clue they have given? So you have to convert, it is read up to 2 volt. So that you have to write instead of that volt V which is equal to 2V, that is equal to Ig into G plus R3. Instead of that R, here we are using the resistance R3. So that R3 will come. Then V which is equal to Ig G plus R1. So by comparing that, we will get as usual the value like 2 which is equal to G plus R3 by G plus R1. By applying the value of R3 and the value of G, you will get R3 which is equal to G plus 2R1, that is equal to R1 minus 2R2 plus 2R1. So that you will get R3 which is equal to 3R1 minus 2R2. So the R1, R2 value which we need to it, the galvanometer, the converting galvanometer should read up to 2 volt means you should have the value of 3R1 minus 2R2. So next question, a circular coil of wire which is consisting of 100 turns, each of radius 8.0 centimeter, that carries a current of 0.40 ampere. So what is the magnitude of the magnetic field B at the center of the coil? The question you have to write first given from the question. They have given a number of turns, 100 turns they have given, number of turns. And R, the radius which is equal to 8.0 centimeter, or you can write 8 into 10 power minus 2 meter. I value they have given 0.40 ampere. So here, to know about the magnitude of the magnetic field B, so formula B which is equal to mu naught Ni by 2R. The formula if you applied, you will get the value. Mu naught value is what? 4 pi into 10 power minus 7. Right. So by applying the value, you will get 4 pi into 10 power minus 7 into 100 turns. I value which is equal to 0.40 whole divided by 2 into 8 into 10 power minus 2. Right. So by simplifying this, you have to simplify to get the answer. You have to simplify, you will get 3.1 into 10 power minus 4 Tesla. So this is the magnitude of the magnetic field B at the center of the coil. The next question, define the following using suitable diagrams. Number 1, magnetic declination and angle of dip. So in what direction will a compass needle points when kept at the poles and the equator? The first definition and the diagram we can see, magnetic declination. Magnetic declination, we can say that the angle between the magnetic meridian and the geographical meridian. See the diagram, children. So this is the angle of declination diagram. This is the angle between the magnetic meridian and the geographical meridian. So this part only, the magnetic declination. So next one is angle of dip. Angle of dip, which says that angle between the total magnetic field of the earth which makes the surface of the earth. We can say that this is the angle of inclination, or we can say it angle of dip. So this is the total magnetic field BE with the horizontal component, we can say. So that we can write that the angle of dip, which is nothing but what? It is the angle which the magnetic needle which makes the horizontal in the magnetic meridian, or that we can say the total magnetic field which of the earth makes with the surface of the earth. So this is I, magnetic angle of dip or inclination, we can say that. The second part of the question which says that in what direction will a compass needle points when it keeps at the poles and the equator. See, the direction of the compass needle, we can say that it is vertical. Where it is the vertical, that is at the poles. We can say that it is vertical at the earth's surface at poles, and it is parallel in the equator. So that the direction of the compass needle is vertical to the earth's surface at poles and parallel to the earth's surface at equator. Next question. Derive an expression for the magnetic moment of an electron revolving around the nucleus in terms of its angular momentum. What is the direction of the magnetic moment of the electron with respect to its angular momentum? See, the angular momentum, that is mu, which is equal to Ia, right? So this we can write, or else mu, which is equal to, instead of that I current, EV by 2 pi r, it is at the area A, which is equal to pi r square. So we can get mu, which is equal to EV r by 2. See children, as we know that L, which is equal to mvr, from this we can get Vr, which is equal to L by M. Here the magnetic momentum mu, which is equal to minus Ei by 2m from the derivation we have taken. So we can say that the direction of mu, that is magnetic momentum, is opposite to that I. So this is opposite to that I because of the negative charge. Because of this negative charge, we can say that the mu which is opposite to that I. Yes, students. So far we have learned from this session, Chapter 4, Moving Charges and Magnetism, Chapter 5, Magnetism and Matter. So we have seen that which are all they have deleted for this year 2020-2021, and the formulae which are all you have to focus, that we have seen, and the various questions which are asked in the previous year sample papers, previous year question paper, board question papers and all we have discussed. You might have understood. Please practice well, children. All the questions repeatedly practice. Thank you, students.